So, good afternoon, everyone. I want to thank the organizers for inviting me. So, today I'm going to share with you a part of my work which is very different to what you do, guys. So, this is related to multi-layer neural networks based on Spintronic radio frequency devices for the classification of radio frequency signals. So, artificial neural networks are ubiquitous. You can find them in a lot of fields. You can find them in, for example, computer vision, such as image classification or object detection. You can find them in natural language processing, when you can have sentiment analysis, a language modeling. Maybe you heard about GPT-3, which is a big language model. Also speech recognition, etc. But you can also use them to classify radio frequency signals. It can be applied in the medical field, like tumor detection or cancer detection or gesture sensing. In my case, I will only consider the radio frequency fingerprints of drones. So, just a quick introduction on what are artificial neural networks. So what you have is basically a collection of neurons that are interconnected with synapses. Mathematically, synapses correspond to numbers that are the parameters, and the neurons are nonlinear functions that are called activation functions. Basically, those parameters are usually randomly initialized with certain distribution normalized, normal distribution, sorry. And this basically needs to be trained, meaning we have to change those parameters if we want to perform a certain classification task. So what you have is training data first, which will be used to train the model. In the case of supervised learning, what you have is label data, meaning that you always have a certain label which is associated to each input data to clearly identify to which classes each data belongs to. Each training set is basically composed of several classes. In this case, this is a really known data set, which is called MNIST. It is based on n-written digits. And you basically have all the digits, so ranging from 0 to 9. So you have 10 classes. Now, what you do with those inputs, which is in this case images, you basically take each pixels to which is associated a brightness value. And each pixel will constitute your input for the networks. Now, this will run a certain mathematical, nonlinear mathematical operation until you get, at the end, a certain number of outputs, sorry. The number of outputs depends on the number of classes you consider in your training set. Meaning that, for example, if I have the seventh nodes, which correspond to the highest score number, this corresponds to the predicted class. And obviously, as I said previously, when you initialize your neural network, usually it will give you wrong predictions. So you have to train it, and in order to train it, you use a learning algorithm that will take care of the label and the prediction and calculate the updates of each parameters accordingly. Now, artificial neural networks are implemented in classical hardware. So what do I mean by that is the classical hardware is based on the von Neumann architecture. So we consider two different things, a memory unit and a processing unit. And there is some exchange of data between those two. The thing is, with that kind of architecture, the performances is limited by those exchanges. So this is what we call the von Neumann bottleneck. And we can also see on the table here that these exchanges, which correspond to accessing the data in the memory, basically, cost a lot of energy if we compare to a single operation. Now, why it could be problematic in the case of neural networks? Well, as the time goes by, you have the models, neural networks, that became more and more complex, having more and more parameters, because they are considering like more complex tasks. And so the thing is that if we have a high number of parameters, it means that we have a higher memory usage, hence higher energy consumption. So we would like to reduce this energy consumption eventually. So this is why a certain interest for neuromorphic chips this is why we are interested in neuromorphic chips that are based on in-memory computing. So this time you just get rid of the exchange of the data. You just merge the memory and the processing units together. And so here is a simple comparison of the power efficiency during the learning phase. And what you can see is that for the classical hardware, you do have the GPU that have a better power efficiency compared to the CPU. But if you consider neuro-inspired computing chips, also based on, this time, CMOS technology, you can increase this power efficiency. But if we consider other nanotechnologies together with this CMOS, you can even gain order of magnitudes in power efficiency. The advantage of novel technology also is that we can get more compact devices that will allow the embedding of neural networks in little chips, not like in a cloud, for example. So in this talk, I will show you how we can use the radio frequency dynamics of magnetic to-knock junction to create synapses and the neurons that are the basic component of neural networks. So artificial neural networks are based on two basic operations. So if, for example, you consider a single unit right here, it's like you have a collection of inputs, the synaptic weights, and there is a sort of operation which is the weighted sum of the inputs. This is the synapse part, let's say. Now, this weighted sum is considered as an input of the neurons, aka the activation function, which is usually nonlinear. Now, mathematically, it simply corresponds to this. So you have the output of a neuron. And if you want to construct a layer of a neural network, what you do is simply stack those little architecture, let's say. And what you get at the end is an output vector. You simply have a vector matrix product here where W stores all the weight of the layer. To complexify even more, we can create deep neural networks, which is simply the composition of the previous operation. And this is something we actually want to create deep neural networks because those networks are capable of solving really complex tasks. So I will show you how can we build these two basic operations using magnetic to-knock junctions. So if we consider an input radio frequency signal to the magnetic tunnel junction, what you get is a DC voltage which can be modeled as an anti-Lorentzian right here, which depends on material parameters such as the Gilbert damping, the resonance frequency of the magnetic tunnel junction, and also the input frequency. Here, I just represent this anti-Lorentzian, which is simply the voltage as a function of the input frequency for a resonance frequency of 200 megahertz. What we can also see is that as we increase the power of the input signal, what you get is actually a linear increase or decrease of the voltage. This is represented here, and here we can therefore see a first idea of a weight, like you have an input power which is weighted by this rectification function. So in order to get the weighted sum, what we do is we can connect MTJs electrically. Here I consider, for example, a signal which is composed or created by frequency multiplexing. And it is injected into a chain of MTJ. And what you get is basically that each resonator will rectify each input signal. And this gives us the first building block, which is the weighted sum of the input powers. Now, to each chain, I will show you that it is associated a neuron. So how do we build neurons? Oh, sorry. So a neuron is simply a magnetic tunnel junction to which we inject a DC current in it. So the magnetization will process. This will give you an oscillation of the voltage, and actually the output power of the resulting signal is expressed as a function of the current here, gives you this nice nonlinear function here. R is the electric resistance, and I is the threshold current necessary for the oscillator to auto-oscillate. So now we have our two basics operation, and we can build our deep physical neural network. So we have the weighted sum, which corresponds to a chain of resonators, and the activation function, which corresponds to one MTJ with a DC current in it. And what you can do is stack those little building blocks to create layers. And you can also interconnect those layers to create deep neural networks. So now I would just want to show you quickly that we did at the lab, not me, it's actually my colleague, Andrew Ross, and Alice Misery and Nathan Leroux, who did an experimental demonstration of a small neural network. So in this case, we only consider two layers with two hidden neurons. So you can see the full architecture here. And the task they try to solve is simply to separate two different values of power for the output MTJ, which is the power it is either equal to 0 or different from 0. So red for different, blue equal to 0. These are nonlinear tasks that were used to test the experimental model. This is actually the result of the simulation. This is what we are supposed to get. And this is the result of this little circuit. So we can see that some points are misclassified, but overall it is doing a pretty good job solving this task. Now, we would like to treat more complex task and also consider like a greater neural network. We want to simulate those because we can't yet doing it experimentally. So this is where I come into play, let's say. First, I will just explain the task we considered. So we want to classify radio frequency fingerprints of drone signals. So we use for this a database that was elaborated, and it is available through this reference. You basically have 10 classes. You have signals of drones that we take directly, and you can inject them into the deep neural network. And basically what you get is that as the output voltage, the higher the output voltage, the highest, output voltage gives you the prediction of the neural network. So in this case, for example, the second NTJ will correspond to the drone of class 2. An advantage of radio frequency spintronic devices in this task is that, contrary to when we consider a software part, when you can do this task as well, you can actually avoid one step in the treatment. So, for example, you first receive a certain signal. You can do some frequency translation in order to sample the signal through digitization, and then you can process the signal. By considering radio frequency spintronic devices, we can directly consider the RF signals. So we get rid of this digitization, which is usually what costs a lot of energy in this process. I simply show you here how the data set is looking like, let's say. So you have 10 different classes, and this is the type of inputs you inject into the network. The frequency range corresponds to 20 and to 120 megahertz, because we have to respect the bandwidth of the Wi-Fi signal, which is 100 megahertz. Quickly, what I've done is I implemented a simulator that can do any architecture we want, I mean as deep as we want. And I use a framework which is open source, which is called PyTorch, which is used a lot in machine learning. I implemented also the analytical model for the synapse and the neurons. And I consider for this work a specific architecture, which is composed of 128 hidden neurons, which correspond to the center, and of course 10 output voltages, because we have 10 classes. So here on the left side, I plot what we call accuracy. It's simply the number of counts or good counts when you classify, let's say, the images, the signals right. And this is as the function of epochs. Epochs means simply that you train your model over the data several times. Each time you have inserted the whole data set, you just repeat. And this allows you to increase the accuracy of the model. So here I compared the physical model with the software one. And what we can say is that actually the performances are quite close to the software one, which is really promising. Actually, it's satisfying to see. It's like, it seems to work. To go further, what we can do is try to avoid any pretreatments such as frequency translation. And for that, we simply inject the signals at the Wi-Fi band range. Unfortunately, let's say, we have a little loss of the accuracy of the model, but still it is 95% accuracy, and we still need to improve a little bit the results, so still encouraging. So in order to explain why the accuracy gets a little bit worse, we tried to plot the weights. We plotted the weights of, for example, one chain. You take one chain and you plot the weights associated to it. What we can see is that there is dots everywhere. It doesn't seem to be really correlated. Maybe you have some correlation here, like a certain behavior. This corresponds to the case of the software model, when there is no real correlation between the dots. However, in the case of the gigahertz range, what we can see is that there is a clear correlation between the weights. So we're still trying to explain why it is occurred, but one clue is that when you consider the rectification function, what you have here is the line width. And as you change the range of frequencies, this line width is increasing. What does it mean? It means that in the case we consider a chain and simply the first 4 resonators, you can see that the overlapping region amplitude might be not as important as in the case of the gigahertz range. Well, the range of rectification is quite wide compared to the case of the megahertz range. So there is probably a sort of the coupling between the weights is intensified by the fact that it is overlapped. The overlapping is increasing, sorry. So just to conclude, I showed you that neuromorphic chips can contribute to reducing the energy consumption of machine learning applications. It's general. More specifically, we can build a deep physical neural network using magnetic tunnel junction for both synapses and neurons. We perform a classification task on a data set of real radio frequency drone signals with a similar performance as the software model, at least for one specific range of frequencies. I did not talk this in my talk, but this is a new estimation of the consumption of energy, which is estimated around 100 femtojoules per neuron and 10 femtojoules per synapses. So it gives you an idea, the order of magnitude we could gain compared to the classical hardware, about 100 times less energy. Now, if we want to go further, we could explore other architectures, more complex, to see if we can improve the performances for the second case. And we can also consider other tasks, more complex tasks, classification of medical signal, for example. And that's it. If you have any questions.